Provost, and it's my pleasure to welcome you today to the Senior Research Symposium. First of all, I want to be sure to thank Karen Fries and Kim Flinchbaugh from the Clark Forum, who were very helpful in organizing all of this and advertising it and doing the posters and the programs that you have today. And also thankful that we're able to put this into a common hour so that we know that lots of folks on campus are able to be here to hear what you have to say today. We will have 6 seniors who are going to present their research, and from those 6, the top 3 will be selected as our winners of our Senior Research Symposium. So in order to have winners, we have to have judges. So I want to introduce to you our judges today. Jessica Wahman from Psychology, Jeremy Ball. Oh, Psychology. What? Philosophy? Oh my gosh. I had psychology on my mind this morning. Jessica Wahman from Philosophy, Jeremy Ball in History, and Christy Humphreys in Chemistry. So our format today is very simple. Each student will give their presentation. They'll each be about 8 minutes. They will introduce themselves as part of that presentation. We'll do one right after the other. You'll need to write down your questions and keep track of them, because we're going to hold all questions until the very end while are deliberating. So we're ready to begin.
All right. Good afternoon. My name is Mark Veranda, and this is a project I did for Honors in Computer Science. The name is Applying a Genetic Algorithm to the Localization Problem Using an Extremely Sensing Limited Robot. My advisor was Associate Professor Grant Brott of the Mathematics and Computer Science Department. And anyways, I'm sure you're wondering, what did I just say? So the localization problem, I guarantee you've probably done it at some point in your life, and that is finding your location on a map. So if you've ever been in a city and you have a map of the city and you need to find out where you are in the city, that's the localization problem. Extremely Sensing Limited Robot is basically a robot that's been built with as few and as cheap sensors as possible, and I'll get to that in a minute, why anyone will want to build that. And before I go on, genetic algorithm is basically a search technique that is based upon evolution. So you can think of survival as the fittest, and what exactly do they search for? They search through a set of guesses, looking for the best guess to some problem. So in this project, the problem is the localization problem, and the best solution is the actual location of the robot. So why worry about localization? The first thing that people ask me is, what about GPS? I mean, doesn't that work perfectly fine? It tells you right where you are. And to that I say, what if GPS breaks down? What if the satellites get shot down? What if your GPS receiver gets shot out, or you're underwater, or if you're even on another planet, GPS doesn't work there. So you need some sort of backup for GPS, which is where this project is important and why using ESLR. So first of all, they're cheaper to produce, so if you need to build lots of them, that comes in handy. And second of all, so this right here is the winner of the 2005 DARPA Grand Challenge, which was a 40-mile race to the desert of driverless cars. They were all robotic, and the winner won $2 million for the Carnegie Mellon University team. And now I say to you, what if these sensors fail and no sensors fail? And that thing by the wheel well there, it says drivers not required. Clearly you're going to need drivers now. And that's the only sensor that survived. This robot here effectively becomes this robot, which is the Extremely Sensing Limited Robot that I use for my project, which is called the Hemison robot. It's built by K-Team, a Swiss corporation, and it has a single sonar. So there, it has one sonar. Here it has one sonar. And the green battery is rechargeable. That's good for the environment. And you can see it's pretty small, so right. And the objective was simply give the robot a map, and it will be able to use this algorithm, this genetic algorithm, to find out where it is on the map. So the way to do that is the genetic algorithm will search through the positions in the map, looking for where the robot could be, effectively guessing and checking. So what's a good position is where the expected sensory data is matched to the actual data that you're getting. So if you predict you're in some position that's 20 inches away from a wall and your sonar device is saying 20 inches, you could possibly be in that position. Now the major problem with this is sensor aliasing. So suppose I give you a map of Dickinson College and you need to find out where you are. So you look up from your map and you see this. I'm pretty sure most of you agree that this is where you would be. Now, however, what if you're to look, and this is all you see? A limestone wall. I think most of you would be hard-pressed to find out where it is. It could be here, and it could even be the previous location where you were just, which I just showed. And I actually took that on Britain Plaza, but anyways. And that problem is called the sensor aliasing problem, where two different positions provide the same sensor data as, so two different positions provide the same sensory data. So they look the same, just like that limestone wall. And for the robot, that would be, so here's the setup I gave of the robot. That's where it actually was, and this was the map given to it. So if the robot needs to find out where it is, and its sensor is telling it's 16 inches away from some location, any of these positions that are 16 inches away from a wall